Hello, I'm Joel Swerdel, and today I'm going to be speaking about our study, developing a benchmark for empirically evaluating the performance of phenotype evaluation tools. There are three main sources of bias in estimation studies: confounding, selection bias, information bias. OHDSI has analytical tools such as large-scale propensity score adjustment and empirical calibration using negative controls, which aims to reduce error due to confounding and selection bias. But we have not advanced as much in handling the risk of error due to information bias. Information bias is a problem not only in estimation studies where the goal is to produce an unbiased effect estimate, but also in prediction models if we misspecify our target population or outcome, or even in characterization studies when we try to understand the prevalence of baseline characteristics in disease natural history, or the incidence of outcomes within populations of interest. In studies, we use phenotype algorithms to define our outcomes and exposures in our studies. We need to assess whether the performance of these phenotype algorithms, including their sensitivity and specificity. Traditional methods for evaluating these phenotype algorithms, such as patient chart review, are expensive and often do not provide the full set of performance measures. We would like to evaluate the performance using a tool which would be more efficient while providing the full set of performance characteristics. But how do we know if the tool is providing the correct answers? The objective of our study was to develop a benchmark to allow comparisons between different tools and traditional performance validation. A literature search was conducted on 18 selected phenotypes based on a broad range of conditions and therapeutic areas. The goal was to find and extract phenotype algorithm performance characteristics, namely sensitivity, specificity, positive predictive value, and negative predictive value. We chose studies of traditional validation based on specific criteria, including requiring a clinician to review charts and requiring a protocol. We specifically sought to find studies which reported the full set of performance characteristics. While some studies reported sensitivity and specificity, many times these were not determined correctly. For example, in many studies, sensitivity was determined using the algorithm for one code of the health outcome as the full population, and determining sensitivity of the more complex algorithms as the fractions of subjects included in the one code algorithm. Here we see the results for positive predictive value, PPV, across the studies in our benchmark. Overall, we used 18 phenotypes and 94 phenotype algorithms. These 18 phenotypes came from 5 therapeutic areas: oncology, neurology, infectious disease, immunology, and cardiovascular disease, from 36 studies, and from 6 countries: Australia, Canada, Denmark, France, the UK, and the US. While all reported PPV, only 8 reported sensitivity and 4 reported specificity, as shown by the stars in the diagram. We found a wide range of PPV values from 20% to 99%. Of note is that we found that 1 out of 6 of the validated algorithms had PPVs less than 50%, meaning that common algorithms that we all use got it wrong more than they got it right. In this slide, we show an example for rheumatoid arthritis. For rheumatoid arthritis, we found 3 studies with 13 algorithms tested. Results for PPV range from 31% to 91%. Of note here is that the algorithms with the highest PPVs, one was for an inpatient visit for rheumatoid arthritis, a condition which generally does not cause one to be hospitalized, and one required many inclusion criteria. These 2 studies speak to the need for a validation process that includes estimates for sensitivity, as these likely included only a small portion of those with rheumatoid arthritis. Here we show differences between studies testing the same algorithm. For example, in 2 studies examining the performance characteristics for epilepsy using an algorithm of 1 code in an inpatient setting, one study found a PPV of 70%, while another study found a PPV of 99%. And in 3 studies using an algorithm of 1 code for psoriasis, the values for PPV range from about 40% to about 90%. So one of the studies says the algorithm got it mostly wrong, while another study says the same algorithm got it nearly all right. In conclusion, in our study, we created a benchmark, a target to assess the performance of phenotype algorithm evaluation tools. All the data for our benchmark may be found in the OHDSI GitHub repository, including extracted statistics and links to the original studies, as well as the JSON files for each of the algorithms examined. We reviewed 36 studies evaluating 94 phenotype algorithms and found a wide range of values for positive predictive. It's important to note that most studies only provide PPV, which is generally insufficient for performance assessment, underscoring the need for a tool that will provide the full set of performance statistics, particularly sensitivity and specificity. Our next steps will be to test Phevaluator, a tool within the OHDSI toolkit developed for phenotype algorithm evaluation against the benchmark. We invite others to use the benchmark to test other performance evaluation tools. Thank you, and I'll be open for questions during the Q&A session.